Hi, I'm Barry Holben. I'm Vice President Sales of Allen Organ Company, and today it's my pleasure to show you the manufacturing facilities of our company in Macungie, Pennsylvania. Before we get to the factory, I'd like to show you a little bit about the products that we manufacture, and the instrument to my left is a 3-manual Allen organ that I'm going to play for you briefly. These instruments have become very popular throughout the world. We export to countries around the globe. And the reason for our company's success is our ability to produce pipe organ sound using modern technology at a fraction of the cost of a comparable pipe organ. The instrument that you see is built from the ground up in our factory. The console starts as raw wood, and we build, in addition to the console, all of the electronics that go inside of it, the keyboards themselves, the amplifiers that power the speakers, and the speaker enclosures themselves. So we are a traditional, old-school, vertical manufacturer building the entire product, not just a final assembler. We've been in business for over 75 years, and through that time period, we've used a variety of different technologies. In the early days, we used vacuum tubes to produce the sound, and then in the 60s, we built organs that used transistors. In the 1970s, we really started a revolution in technology when we produced the first instruments in the world that made sound using digital tone generation. I'll tell you more about that in a few minutes. But for right now, let's just see what these things sound like. You've probably heard the old expression, pulling out all the stops. That actually comes from the organ. And each of these buttons on either side of the keyboard are called the organ's stops. If you look closely, you'll see that they're engraved with the names of different instruments. This one is called an oboe. Let's see what it sounds like. And we've got trumpets. But there are a lot of stops on the organ that don't have the kinds of names you might expect in an orchestra. This one, Rohr Borden, describes a specific type of pipe that's used in a pipe organ that sounds like this. When the air enters the pipe, you hear a little chiff of wind at the beginning of the sound until the sound wave is set up and stable inside the pipe. And we can recreate all of those details. Now, I told you that an Allen organ produces pipe organ sound at a fraction of the cost of a real pipe organ. And to put that in a little better perspective, in a pipe organ, to produce each of the 61 notes on this keyboard, we'd need 61 pipes, each of a different length. The longest one, down here, would actually be 8 feet long, and that's where the little numeral 8 comes from on the draw knob face. 8-foot pitch, and with each octave, the pipe goes to half length. So this pipe would be 8 foot, that one would be 4 foot, that would be 2 foot, 1 foot, 6 inches, 3 inches long. And you can imagine those 61 pipes up in a pipe loft someplace. And in today's world, just one stop of pipe work, each of those pipes is made by hand, one stop can be $12,000 or $15,000. So if this were a pipe organ, you can do a little rough math and multiply each of these knobs by $12,000, and you can see that a sizable pipe organ could be easily $500,000 to $1 million, and in today's world, that cost is unobtainable for most churches who are our primary customers. So instead, we are able, through modern technology, digital technology, to produce pipe organ sound, and we use speakers and amplifiers and digital tone generation to create the sound of a pipe organ without all of the cost. Let's see when we put some of these stops together, what it sounds like. while I was playing that piece of music, I was using my hands to pull out different stops, but the organ also has these little buttons between the keyboards called pistons, and they allow you to do the same sort of thing by remote control. So while you're playing the keyboard, you can also reach down with a thumb and press one of these pistons and change the registration. Today's technology lets us not only create the sound of the pipes, but the sound of the room itself. And in this recording, in this performance that I just played, I was just using the actual, you were just hearing the actual acoustics of this room. But I can add the acoustics of a huge cathedral, and the sound reverberates as if we are in Saint Denis in Paris or some other large cavernous space. And that space and how the space reflects the sound is part of what many people think of as being pipe organ sound. It's actually how the sounds of the pipes are reflected and reverberated by the building in which they're located. So in smaller American churches, it's virtually impossible to get this kind of reverb from the building itself. Let's listen again. But that reverb is what the great composers of different historic periods in Europe experienced when they listened to pipe organs. And so they created music that would use that acoustic to help create the musical effect. Most people know this piece of music for the pipe organ. It's a famous French toccata. Part of the beauty of that piece of music is listening to how the sounds ripple in the air and reverberate. And so we create the same effect using our modern technology. So it's not just the sound of the instrument, but the sound of the room that helps make our technology so effective. Well, that's a little bit about how the organs sound. I'd like to take you to another location and show you a little bit about the history of our company, and then after that we'll go to the factory and see how they're built. This is the Jerome Markowitz Memorial Center. It's a museum that honors the memory of our company's founder, and it chronicles the development of our products from the company's beginning to the current time. And Jerome was an inventor and a tinkerer, and through his lifetime, he and the company that he led wound up holding more than 100 patents in sound production and related technologies. So what you see here is the remnants of the very first organ that Jerome built. This was the tone generation, and if you look closely, you'll see a lot of vacuum tubes. Hardly anything uses vacuum tubes anymore, but we still provide service for instruments of this vintage, and there are still several of them out there serving customers today. We're very proud of the product support that we offer, and to my knowledge, we're the only manufacturer of any kind of electronics that's still supporting instruments that are 70 years old. The very first instruments that Jerome made and the very first patent that he held was one that used a stable oscillating circuit to produce a tone. And that was the centerpiece, the cornerstone for the very first electronic organs. This assembly that I'm holding was used as tone generation in instruments built by our company in the 1960s. There aren't any vacuum tubes on it because by the 60s, vacuum tube technology had been surpassed by transistors. The little tiny silver cylindrical components on this board are transistors. And the transistor, coincidentally, was developed and invented not far from here in Allentown by the Bell Labs. And when we started to use transistors in our organs, the efficiency of transistors and their capabilities contributed to a great increase in our company's success. Through the 1960s, Allen organs began to be exported around the world, and some of the instruments on display here have a very rich significance. You'll see a scale model here of an instrument that was built during that time, and it was installed in the United Nations Chapel in New York City. This instrument is the very instrument that was used for the opening of Lincoln Center. Lincoln Center at that time had purchased a pipe organ for the facilities, but the pipe organ was not yet completed and was unable to perform in the opening ceremonies. And so Lincoln Center asked us to produce an Allen organ for them, or provide an Allen organ for them. And in the newspaper the next day, one of the critics that reviewed the concert made some comments about how wonderful the new pipe organ sounded in Lincoln Center. He obviously didn't realize that the pipe organ wasn't playing and it was an Allen organ instead. Both the vacuum tube technology instruments and the transistor instruments that I've shown you fall into a category called analog. The technology of that day used electronic circuits to imitate what was happening in a pipe. And the imitation was good, but it wasn't quite perfect. And in the late 60s, we partnered with North American Rockwell in what became a revolution in the music industry. North American Rockwell had been contracted by NASA to develop the miniaturized computers that needed to go into the Apollo spacecraft and would time the firing of the retro rockets to get the astronauts back into the Earth's atmosphere safely. The timing of this sequence was very important because if it wasn't done exactly the right way, one of two very bad things happened. The return module would go into the atmosphere too quickly and burn up, or it would enter at too shallow an angle and bounce off. So the computerized control was of paramount importance. After Rockwell developed the miniaturized computer for NASA, they looked for other applications for that technology. By the way, until that technology was developed, computers were huge things. They were the size of railroad cars. They took up entire rooms, and it wasn't until Rockwell came up with a way of shrinking that circuitry into a very small area that the computer could be small enough and light enough to go into a space capsule. That was the beginning of all PC-related and digital-related technology that we use in our phones and on laptops and in iPads and every kind of computerized device. One of the things that Rockwell found was that they could store a sequence of numbers and then reproduce events using that same sequence of numbers. And they came to us and proposed that we would develop together a musical instrument that used that technology. And when Jerome Markowitz saw the potential that digital technology held, he literally bet the ranch on it. He was a very conservative businessman, but at that moment he saw this was the future of music. And so we plunged into a 3-year-long development project with North American Rockwell, and this instrument in back of me was the engineering model. As I said, up until this time, all musical instruments, all electronic musical instruments made sound using analog technology, and it was an imitation of the natural event that we were trying to replicate. But with digital technology, you could take a sound, measure it, turn it into numbers, store those numbers in a computer, and then use those very same numbers to reassemble the sound and recreate it with the same authenticity that a photograph recreates the object that's photographed. everything up until this point was like a Van Gogh or a Rembrandt painting. Beautiful to see, but not exact in its detail. What we created here was more like an Ansel Adams photograph. And we used state-of-the-art technology for the 1970s. And in that technology, a circuit board of this size was shrunk photographically down to an area of this size, a very small square. 3,000 transistors could fit into a small square like that. This instrument is one of the very first Allen organs to be built with digital technology. The actual very first instrument, and you'll see it in this photograph, and you see it looks very much like the one here in front of me, that instrument is now in the Smithsonian. And that's because the Smithsonian agrees that the historical significance of this instrument was quite fantastic. And pictured in this photograph is Jerome Markowitz, his widow Martha, and the other gentlemen who were part of the management team of Allen Organ Company at the time that digital technology was unveiled. This is Eugene Morose. He was the plant manager. John Daniel, who actually sold the very first digital instrument. Bob Pierce, who was the vice president of sales. And Leonard Helfrich, who was the company's treasurer at that time. Now, the digital technology we're using today is generations beyond the technology of these instruments. And to use the analogy, if this was like a handheld calculator, what we build today is more like a supercomputer. As a matter of fact, the instrument that I played for you at the beginning of this tour actually uses the computing power of about 30 PCs. So it really is a digital supercomputer. Now I'd like to take you to the factory, which is about a half a mile from here in Makunji, and show you how these instruments are built. This is the Allen factory, and under a single roof in this facility, we do electronic assembly manufacture, carpentry, final assembly, sheet metal work, all of which are like separate little factories under the same roof. The first place we're going to go into is the electronic assembly manufacturing facility. This factory was actually started as a textile manufacturing facility and was purchased by Allen Organ Company in the 1950s. So this portion of the factory has been renovated, and what you'll see is something very similar to a clean room. It's got its own air handling system, and it's got an anti-static floor, and I'm wearing this special white coat because that's one of the regulations for going into this area. Let's go ahead and see what's happening there. There are a number of different procedures that take place in this portion of the factory. Of course, we manufacture parts for new instruments, but we also refurbish parts for instruments that are in the field and have required service. By offering refurbished parts, we keep the cost of in-field service down as low as possible. After every assembly is built in the factory, it is also tested in this area. And so if it's necessary to repair an assembly that's been shown to have a fault in testing, that's done in this area as well. The machines in the far corner here are actually computerized test facilities, and they will run an assembly through a complete functionality test, and if there are any problems, those computers will produce something that looks sort of like a grocery receipt. It's a list of the locations and the components that need to be repaired. So every assembly is tested when it's built, and then the assemblies, once they're installed in an instrument, are tested again. And components are also tested. So we have triple layer of testing and quality control for every instrument before it even ships from our factory. Years ago, a circuit board like this one would have had one layer of circuitry. And with one layer of circuitry, the components could be inserted into holes in the board and then soldered from the outside. By today's technology, boards like this can have 5, 6, or even 7 layers of circuitry, so that what you see on one side of the board is entirely different from what's going on the other side of the board. At the same time, components have become much smaller and more densely populated on the board. So it's become almost impossible to manufacture boards by hand anymore. And so instead, we're using some very sophisticated machines like the one next to me. It's called a pick and place machine. And just as the name implies, little robotic arms will pick the individual components off a reel of tape and position them on the surface of the board. The surface of the board, before it goes into the pick and place machine, is coated with a mastic. And each of the components is placed on that mastic. After they're placed, the componentry, the assembly, goes through an oven which cures the mastic. Let's see how that works. You'll see the board is moving underneath the insertion head, and the insertion head first takes the individual components off these reels of tape, and then through the control computer program places each component where it needs to be positioned on the board. There the head is taking the components off the tape. Here it's positioning on the board. Off the tape and on the board. After the board's been assembled, it goes through a conveyor belt oven like this one, and the mastic on the board is cured, and the board's complete. The next step is inspection, and that gets a little more complicated because there are so many layers of circuitry and the complexity of the componentry is so dense. Let's see how we inspect something that we can't really visually see. Sometimes your doctor needs to take an X-ray to see what's going on inside of you, and the same thing's true in our manufacturing. The components that we use today have contacts that go directly out the bottom of the componentry and directly into the circuit board. So there's no way to visually inspect them. And for that reason, we use an X-ray machine like this one. It X-rays the substrate underneath the component and verifies that there is sufficient and good soldering at each one of the connection points. Individual components the size of the ones that you see here can have hundreds of soldering points in between them and the solder board. So this step is crucial. The equipment is expensive, but it's necessary to create a good quality product. Just down the hallway from electronic assembly manufacturing is the carpentry shop, where all the woodworking is done. To keep the air as pure as possible, we have exhaust from all of these machines that goes outside of the building to keep sawdust at an absolute minimum. In this portion of the factory, rough sawn wood, like this piece of oak I'm holding, comes in this door, and by the time it moves through this portion of the factory, it's planed and shaped by the machines that are in back of me, and then it's moved to the CNC, computer numerically controlled routers that I'll show you shortly, where it's actually turned into the parts that are necessary to build consoles. So this raw wood, by the time we're finished with it, is going to turn into a piece of an Allen organ console. Let's see how that works. Sanding is an important part of the process of woodworking here in the factory. If you're like me, when you think about sanding, you probably envision a piece of paper wrapped around a block of wood that you move back and forth by hand. But even in the old days, that's not the way we did it here. Let me show you a machine that we don't use anymore, but that used to be the prime sanding machine. This machine has a belt of abrasive material that moves across the workpiece, and the workpiece, the piece that's being sanded, is positioned on a table. That table moves back and forth, and the operator uses this block to exert pressure on the piece so that the sanding is done in this direction and also this direction at the same time. Now, the amount of pressure to apply and the speed with which you move the table is all up to the operator, and the men who use these machines were skilled technicians who developed their skill over years of experience. Today we do it quite a different way. Let me show you a machine that automates the process. This sander is one that we bought from a company in Italy, and it automates the process of sanding. Inside this machine, you see belts of abrasive material that are traveling in the same direction as the work material underneath them, and in the door next, which I'll open, you see another band of abrasive material that moves in contrary motion to the workflow. So we'll put a piece of wood in this end of the sander, and as it comes through, this abrasive belt works on it first, then this one, then the third one. And each successive abrasion is gentler. So the abrasive quality of this last belt is very, very fine. And this last belt is attached to an adjustable roller that can, by an eye inside, calibrate how much material it takes off the workpiece and in which portion of the material, or in which portion of the piece, the material is taken off. So if there's a high spot just here, we can remove just that bit of material and make sure that at the end of the process, the surface of the workpiece is entirely smooth and entirely level. A lot of people don't realize it, but sanding is the first step toward producing a wonderful finish on any piece of furniture. Unless the work is sanded perfectly, it shows up as an imperfection once the finish is applied. This computer screen allows the operator to tell the machine which piece of work is being worked on, and every different workpiece has a different program. So the program tells the sander how fast to move the work, how fast to spin the abrasive material, and the combination produces a perfect result. What you're seeing now is one of our CNC routers in action. This machine has a variety of different cutting tools and drills that can be presented to the workpiece. It's controlled by a computer station to the right of the cutting table, and that computer station has a program built into it for each different type of workpiece. What you'll see is that the cutting heads lift up above the workpiece, and then when the right cutting head is in place, it goes back down to the workpiece. The cutting head is actually surrounded by a brush that keeps dust and dirt out of the cutting area. So you can't actually see the head spinning, but what you'll see above it are exchangers that work kind of like a typewriter that alternate and exchange the various cutting heads while the piece is being dimensioned. The table moves, the cutting heads move, so it's a triple axis or XYZ operation. It can change depth and vertical or horizontal action. Every component that's produced using the CNC router requires a fixture to hold it in place while the router heads and the drills are working on it. What you see here is an indication of all the various different assemblies we create in this part of the factory. Each one of these fixtures is used for one or more different assemblies. This part that I'm holding will eventually be used as a draw knob jam in an organ. And by using the CNC routers, we assure the best and most repeatable way of making parts precisely and quickly and to exact dimensions. After the individual parts have been cut, milled, and shaped, they're brought to this part of our factory called the console assembly area. They're inventoried on these racks, and then eventually they're brought to this portion of the facility where they're turned into pedal boards and consoles. As you'll see, the assembly of a pedal board is done by hand, as is the assembly of our consoles. All of the assembly is done using glue and dowels, as in fine furniture. So our woodworking is a combination of old school and new school. Here we see an Allen console starting to take shape. The draw knob jams that you saw being cut on the CNC router just a minute ago have been partially assembled. They are going to fit into the console on these planes on either side, and eventually the draw knobs will be inserted to them later in the process. You'll see that. I wanted to show you some details about the console quality. If you look at the cross section of the console sides, you'll see that we use hardwood butcher block construction. This is the best, most stable kind of construction that can be used in any furniture. It's much better than plywood or even one solid piece of wood. This resists checking and warping and cupping and all the things that can disfigure or distort a piece of woodworking. On the outside, you see the thickness of the real walnut, in this case, veneer and outside layers that we use. And all of the products being used here are real hardwoods or hardwood veneers. There's no other kind of laminate or engineered wood product. This is all poplar core, and in this case, walnut on the outside. We also use oak as a second wood species that we work in. What you see here is Eric positioning the key beds in the console shell, and next he'll measure them to make sure the placement is accurate, and finally he'll attach them to the console. The aluminum parts that you see are the actual keyboard beds on which the individual keys of the keyboard will be positioned. We'll see in a little while how the individual keys are produced. One of the things that Allen does to make sure the keyboard beds are as sturdy and as stable as possible is that we construct them out of aluminum instead of out of just wood or plastic.
it around those, and we can end it there.
After the keyboards have been positioned accurately, the draw knob jambs are positioned around the keyboards. The keyboard positioning is the centerpiece of the console interior. In addition to woodworking, we also do a fair amount of metal fabrication here in the factory. And this piece that I'm holding in my hand and all of these pieces on these boards are examples of parts that are made by the milling machines in back of me. I'll show you how those work in just a second. Some people think we are obsessive about the level to which we build things in-house, but there are three real reasons why we do it that way. First, sometimes we can actually build better assemblies at a lower cost. Second, we provide a high degree of customization in our products. Organists can literally design their instruments from the ground up if they want to. And by producing the components in-house, we have a much greater flexibility in that process. Lastly, we really pride ourselves on long-term product support. Our warranties are 10 years. And we still supply parts for every instrument that's in the field, regardless of its age. So by having the flexibility to make things in-house, we're not reliant upon our providers who may or may not go in or out of business. In addition to milling, we also bend and powder coat sheet metal covers for a lot of our components here in the factory. This is a power supply cover, and the powder coating has been applied in another area. The operator in back of me is stamping out sheet metal that will be used for another power supply and its cover. By covering all of the electronics with sheet metal like this, we provide a protection from any kind of contaminants or even rodents that can get inside of a console. So these are safety precautions. After the console shell is completed, it's hand trucked to the lower portion of our factory where it receives a hand sanding, a final hand sanding, and then finish is applied. An instrument like this one actually uses two different wood species. This interior, the key cheeks and the draw knob jamb, are made of oak, and they'll receive one finish, and the exterior portion of the instrument is walnut. It requires a different finish. So all of these pieces are hand sanded and then hand finished, and some of our instruments are finished to the custom requirements of our customers. They might send us a piece of existing woodwork from their church or from their structure, and we can match the finish exactly to that. That's what you see here. And in order to accentuate the grain, this finisher is applying a filler coat. You'll see that on the portions of the console where the filler coat has not yet been applied, the grain seems rather light, but after he applies and then removes the filler coat, the grain is going to be accentuated. The opposite side of this console has already received the filler coat, and you'll see that the grain is much more obvious on this side. One of the things that many Allen owners don't realize about their console is that it's been constructed so that the veneers and pieces on this side are exact matches to the opposite side. See if you can remember this wide graining pattern in the middle of this panel and the figuring on this side of the console. Let's walk around to the other side of the console, and I think you will see an exact mirror opposite of those same details. The final step in finishing is to shade the console. And what you see this finisher doing is applying a shade coat and comparing it to the standard for this particular finish. The sample that he's holding in his hand is the standard against which he shades the entire console. An Allen draw knob is itself a work of art and another example of the high degree of custom capabilities we offer to the customer. This particular one that I'm holding has a rosewood shaft and a rosewood face. We offer black, white, a variety of different woods for both the stem and for the face, and we engrave them here in the factory as well. The tray next to me has engraved faces for the stops required for one of our 3 manual instruments, a 343. And all of these engravings were done on the machine next to me. Ultimately, these engraved surfaces will be filled with a color ink. You see here we have a white ink in the completed draw knob. The engravings can be white, black, red, green, depending on the functionality and preference of the stop and the preference of the customer. So let's see how the engraving's done. We've got a laser engraver here that works similarly to an inkjet printer for a computer, and the control program is done from the PC over on the table to the left. That PC knows the names of the engravings that are going to be produced on these wood draw knob faces that are in the engraving machine. That little burst of light is actually the laser engraving one point, and it moves back and forth and bit by bit engraves the various names of the stops on each face. We offer a variety of fonts and styles of engravings, and the customer can choose a number of different finishes and options for just the draw knob faces. Here are some of the more exotic draw knob face designs that we offer. You've already seen the extruded aluminum keyboard beds of Allen keyboards being manufactured. And here we show you the actual key sticks themselves in various degrees of assembly. The key stick starts as a blank piece of wood, and then it goes around the trolley track of this custom-made machine, and at each milling station an additional route or drill is made, or the felt bushings are applied, or the pivot pins or guide pins or contacts
or key surfaces themselves are assembled. But in one ride around the loop here, a key stick goes from start to finish. This area is aptly called final assembly. It's the last step in the process, and the console arrives here empty. The one next to us, as you'll see, is empty. There's nothing inside of it, and the final assembly is about to begin. This instrument is, I think, finished, except for one or two little items. And what you'll see is this console has been filled with amplifiers, power supplies, on this side, AC distribution box, and right here, structure that looks like a server, this is the tone generation of the organ. This is the heart of the instrument. This is where the sound is produced and then mixed, and then it's output through these cables, these white cables, which then go to the amplifiers and ultimately to the speaker cables that power the speakers out in the lofts of the organ. All of the componentry in an Allen organ is modular. That means that it's all connected by plugs, from the tone generation to the individual draw knobs, which you see from the back in here. Everything is on a plug, so an Allen technician, a service technician in the field, really doesn't need a soldering iron to service the inside of an Allen organ. He simply unplugs whatever component needs to be replaced. He sends it back to us. We repair it at a component level here in the factory. He has spare parts in his service kit, and he just replaces the one from the organ with the one from his service kit. It's usually a matter of minutes to do the exchange rather than the hours that you might expect with a product that has been designed with hardwired componentry. And here you see the end result of a lot of the steps that we've been showing you throughout this tour. One thing that we didn't show before is the foil that's on the bottom. This foil and as well as the metal covering of all the various componentry cuts down on EMI, that's electromagnetic interference, the frequencies that can be broadcast by computerized and electronic devices. So that's protective. Here you see the network control system, the router for the various portions of this organ that are connected by network protocols. You see that the interior of the console is all painted and finished. And from the back here, it's a very, very high-tech piece of equipment. When you move to the front, it's a very traditional and beautiful musical instrument. A lot of the best organists in the world play these instruments and never realize what lurks under the hood, the high-tech aspect of that traditional, beautiful musical instrument. And as you go down the line here, you'll see a variety of finishes and options that we've talked about. This instrument has maple draw knob faces and maple center rail and black stops on the center rail, white faces for the draw knobs. The one next to it hasn't quite gotten that far. Here, all the parts that will be assembled inside of the organ have been delivered to the stage. This instrument won't move from now until the time that it's completed. It will stay right here, and it's assigned to a single worker who will then make all of the assemblies, insert all of the assemblies and connect them all. So when this one is finished, it will look much like the one that's just next to it. As we move down the line, we see a variety of sizes and colors. Here's a 5-manual instrument. This actually takes 3 organists to play it at one time. No, it's not true. one organist, but 5 different keyboards to move around on, and wooden draw knob faces, 2 different oak finishes. The one next to it has walnut on the outside, maple on the inside, different kinds of draw knob engraving. So every Allen organ is unique. Everyone is built to the preferences of the owner. Everyone is in itself a work of art. After the assembly of the organ is completed, each instrument is moved into a test room like this one, where it's connected with speaker cabinets, like the ones that will be shipped with the instrument, and it's tested. The sounds are leveled, the keyboards are adjusted, all of the functionalities of the instrument are verified, and that process in itself can take a day for a very small instrument. It can take much longer for a large or custom instrument. This instrument that we're looking at is a custom instrument because it's been designed to operate a pipe organ. As you may remember at the beginning of the tour, I mentioned that part of the success of our company is our ability to create pipe organ sound, convincing pipe organ sound. There's no more acid test of that than putting Allen sounds side by side in the same installation with a real pipe organ. And our ability to produce and compare under those circumstances is so good that an increasing number of our customers are churches and individuals who already own a pipe organ and need a new console. So we will design a console that will operate their existing pipework and provide them some number of digital stops as well. The speakers for the digital stops are usually hidden up in back of the existing pipework, and so the end result is the pipe organ plays, new sounds play and meld with the pipe organ, and the customer seems to have gotten a much larger instrument in the process, not just a new console. This large board that's next to the console is the interface between the console and the pipes. These boards that you see here actually produce the voltages necessary to operate the electromagnets underneath the pipes. Each pipe typically has an electromagnet that opens and closes the air passage and allows the pipe to speak. So when the player presses a note, the electromagnet opens, allows the air to go through. When the player releases the note, the electromagnet closes and stops the sound. So just this board is required just for the translation of the digital information from the console to the analog DC voltage necessary for the operation of the pipes. And in each of our pipe combination instruments, the design and architecture of this board is slightly different. And the layout of the draw knobs necessary to operate the existing pipe organ can be different as well. The relationship with our customers doesn't end when our products ship from the factory. As a matter of fact, it continues for years or decades afterwards. This assembly that I'm holding in my hands is the tone generation from a 1970s vintage Allen organ. And it's just one of millions of dollars worth of inventory that we maintain to service instruments of every age in the field. The room behind me is filled with parts for supportive instruments that were manufactured decades ago. And it's one of many rooms throughout our factory that's filled with valuable service inventory. Our representatives in the field also have service kits filled with service boards as well, so that a part doesn't even have to ship directly from the factory. There are usually boards nearby in the local Allen dealer's inventory that can be used for exchange within hours or days from any service contact from a customer. All of this service support and attention to detail and commitment to quality, I think, is a direct result
of the fact that our company has been managed throughout its history by the same family. The Markowitz family, first Jerome Markowitz and now his son Steve, who is the current CEO of Allen Organ Company, are the captains of the ship. They are the ones who chart the course and continue that commitment to customer service. And I'd like to introduce you to Steve Markowitz and let him tell you a little bit about that in his own words.
Hi, I'm Steve Markowitz, president of Allen Organ Company. I've had the pleasure of being part of this company since my late childhood years when I worked in various departments to learn the trade of organ building. I joined the company shortly after college and became its president in 1991. I've had the pleasure of receiving communications from customers worldwide who are satisfied and have the pleasure of listening and using our products on a weekly basis for their worship services, as well as in some entertainment uses. I've also had the pleasure of being involved with a company that has a very traditional values, not only towards the musical instruments we make, but our relationship with our employees. In fact, we've had probably 10 employees that had over 50 years of tenure. That relationship between the long term and of our customers and employees has been a very symbiotic one and good for the company, the employees, and our customers. It's also been a part of the philosophy that we've used to support our products for decades, even after they've gone out of production. And today we use the most advanced technology to produce very traditional sounds, and that will be the focus of our progress going forward.
On behalf of Allen Organ Company, I'd like to thank PCN for arranging this tour, and like to thank all of you for watching the tour. I hope you've enjoyed it. If you'd like to learn more about Allen organs, please feel free to contact your local Allen representative or call us in Macungie at 610-966-2202 or visit us on the web at allenorgan.com.